Hey there, Newland here. Let's talk elevators. When they're accelerating upward, we feel one way. When they're accelerating downward, we feel another way. And I want to describe that by looking for the normal force in the bottom of the elevator. So Newton was very instrumental in allowing us to use mathematics to describe forces and how they respond to each other. But actually, Einstein described the inside of an elevator when he was discussing how forces in relative situations are the same, meaning if you're in an elevator and you feel a particular sensation, you don't know whether or not you're moving up or down. And we're going to discuss that very thing. So let's start by describing moving upward and accelerating upward, both. And by the way, we care about which way is plus and minus for the acceleration here. Describing the plus and minus for the velocity will not help us. Because we're going to be using Newton's second law, we care about the direction of acceleration being considered positive for this particular problem when you're discussing an elevator. So always consider if the acceleration is up, then that's the direction of positive. If the acceleration is down, even if the velocity is up, if the acceleration is down, then you'll call that the direction of positive. So let's draw our elevator, and it's being held, by a rope. But here's the thing, the human is now just this dot. So what I'm saying is, here's our stick figure standing on the floor. What I want to know is, what's the normal force? That's what you'll feel. The normal force is what you'll actually respond to. How hard is the floor pressing into you and or pulling away from you, which is also possible. So let's do that. Some of the forces in the y, it's definitely ma because it's not zero. It's also not mv squared over r. So we're definitely going to do four scenarios where the sum of the forces is going to be ma. And again, a is going to be positive in the direction of acceleration, which is literally what I'm saying. But that means the ones that are up need to be the ones that are in the direction of acceleration need to be drawn as plus, and the ones that are opposite the direction of acceleration need to be minus. And I erased my normal force there so I could do this, draw a free body diagram. And by the way, I'm not really trying to say anything with the length of these two vectors. I'm not acknowledging which one is bigger or smaller. I'm leaving that alone for a minute. So let's keep doing that now. Some of the force in the y is ma. The ones that are up are positive, that's normal force. The ones that are down are negative, that's mg. And reminder, direction of acceleration is plus. So little arrow here to indicate we're going to solve for normal. And that's going to be the normal's already positive. So mg moves to the other side, ma plus mg. So that means that normal equals m times a plus g. Two accelerations. Two accelerations mean you feel heavier. The floor is pressing into your feet harder than it would be if you're just standing on the surface of the elevator. So you feel heavier. So the acceleration upward means that the floor is pushing into your feet harder than if you were just moving at a constant speed or if you're standing still. Okay, so that's scenario one. Scenario two, you're on your way up now, but now the elevator is going to slow down as you arrive. So this is velocity. Hang on, wait. I drew a plus sign there. That's not what I meant. This is velocity. This is acceleration. But now downward is plus for acceleration. So the elevator is going to negatively accelerate. So it's going to slow down. This is you arriving at your, third floor destination. Here's the elevator again. We won't even bother with the top. There's the dot, mg down, normal up. Those are still the only two forces you feel, or the only two forces that are acting on your feet on the floor. The normal force is what you feel, though. So when we do the sum of the forces in the y direction, we know this is ma because all of them are ma. You're accelerating, but this time the acceleration is down, which means mg is positive and normal is negative. So now when I go to solve for normal, I have to move it over to the other side and move the ma to this side, and that gives me mg minus ma, or normal equals the mass times g minus a. So this time you're going to actually have acceleration counteracting your weight. So you're going to feel lighter. And this is just at that moment when you're arriving at your floor. And in both cases, when the elevator begins to move and you accelerate and you feel a little bit heavier, your knees kind of sort of want to buckle a little bit. That feeling in the pit of your stomach of accelerating upward, you can definitely tell that's happening. And the same is true as you arrive at your floor. I'm going to go ahead and draw the top of my elevator. When you're arriving at your floor, it's the same scenario. You have that feeling in the pit of your stomach like you're just a little bit lighter than you were, almost like free fall. So it's a bizarre little feeling, and one of the reasons why I don't like elevators. So then finally you go do whatever you're doing on the third floor and you get back in the elevator, and the elevator's heading down, and that's velocity. And now the acceleration is going to be down as well. It has to accelerate downward. This is A, but this is going to be minus and this is going to be plus. So it's going to accelerate downward now to take you back down to the ground floor. So we're not slowing down, we're actually speeding up, but you're now moving and accelerating in the same direction. So there's our dot representing our feet. There's mg again. There's the normal force again. Again, the arrows don't mean anything. The length of the arrows don't mean anything here. As we try to reason out which thing is bigger and which thing is smaller, they're just sort of there. So the sum of the forces in the y direction is still ma. We're still accelerating, but now we're accelerating downward. So that means mg is positive and normal is a negative. So that's actually exactly how we arrived at the third floor. So as we leave the third floor, acceleration is actually in the same direction. But this time the floor is moving down. Okay, so let's see what difference that makes. So I'm going to solve for normal to the other side, and then that equals mg minus ma, and then we can factor out the mass, and that's g minus a. You still feel lighter. So the reason is the floor is moving down and it's accelerating, which means for a very brief moment, it's accelerating faster than you are. And so, for just a tiny, almost like a half a second, the elevator pulls out from under your feet a little bit and you feel a little bit lighter. So, anytime the difference of the accelerations, anytime it's g minus a, you're going to feel lighter. Anytime it's g plus a or a plus g, doesn't matter which one is first, then you're going to feel heavier. So, in the case of leaving the ground floor, you feel heavier. In the case of arriving at the third floor, you feel lighter. When you eventually leave the third floor for just a second, you'll feel lighter. By the way, in all three of these cases, eventually the elevator gets to a constant speed. So there's only a brief acceleration in an elevator because it causes discomfort. You don't like that feeling, or at least I don't like that feeling. When you were like 9 and you jumped in an elevator, you were trying to, extend this bizarre reaction. But for most adults anyway, when the elevator is going in between floors, you want it to accelerate only briefly, and the rest of the time, I drew on my graph there, on my equation. The rest of the time, it did it again. You're hoping not to accelerate, or at least I'm not. Okay, so here we are moving down, and we're about to arrive back. This is velocity. We're going to arrive back at the first floor. So acceleration is now upwards again. So here's our elevator. Here's the floor. I kind of ran out of room there. mg is down, normal is up. Notice what I have not done in any of these four examples. I've not included the string holding the elevator because I'm interested in the feeling on my feet. What is the normal force? I'm not trying to describe tension in the cable or anything like that. I'm trying to describe what I feel. So some of the forces in the y direction is one more time ma. But the acceleration is up this time. So that's normal minus mg, which is normal is up, mg is down. I'm solving for the normal force because that's what I feel. And I'm going to move mg to the other side and I get ma plus mg, and normal equals m times a plus g. Again, it doesn't matter which one of these you write first. So that means you're going to feel heavier again, very briefly, while you're slowing down, because now your inertia wants to carry your center of mass at the same velocity you were moving, but the floor is now preventing you from being able to move at that normal speed. It's slowing you down. It's pressing into your feet to make that happen. So you actually feel heavier. So this elevator problem, which is what we've been doing this entire time, is a really good way to describe the equivalence principle. The equivalence principle, which is where principal, not pal. Principal is your pal, right? That's how I remember. Anyway, so when the elevator is moving up and moving down in all of these different scenarios, what you can really say is if someone were in an elevator and they had no context, in these two cases, they would feel lighter, but the velocities would be in two different directions. In the first case and the last case, you would feel heavier, but the velocity is in two different directions. If someone were blindfolded and put in an elevator, and maybe you move up and you move down, and you don't know what floor you're on, you haven't been able to keep up with it. Once the elevator starts to move, there isn't any way for you to determine whether or not your velocity is up or down. So this equivalence principle actually has a lot of implications for the ideas of general relativity from Einstein, but it's a really good, simple Earth-based way to be able to put it in context. If you're accelerating in one particular direction, that doesn't necessarily let you figure out the velocity. So you can tell that you're accelerating, but not that you are necessarily which way you are moving. Okay, so that's how elevator problems work. Um, be sure to review this if it's confusing stuff.